Let's discover why a quadratic polynomial can have at most two roots. We'll begin with the standard form p of x equals ax² plus bx plus c. And remember that quadratics have highest power of 2. A root is any x value that makes p of x equal 0. So we are looking for those special x values. Now we bring in the factor theorem, which says that if r is a root, then x minus r is a factor of the polynomial. So if p of r equals 0, we can write p of x as a times x minus r times another factor. Now suppose the quadratic has two distinct roots, r1 and r2. Then p of x becomes a times x minus r1 times x minus r2. Each of those linear factors carries 1x, so the highest power we can get from multiplying them is x squared. Now, imagine a third distinct root, r3, existed. The factor theorem would require another factor x minus r3, so the polynomial would look like a times x minus r1 times x minus r2 times x minus r3. Multiplying 3 x factors produces x cubed, and that would make this a degree 3 polynomial, not a quadratic. That contradicts our assumption. So a quadratic cannot have 3 distinct roots. More generally, a polynomial of degree n can have at most n distinct roots because each root brings in exactly one linear factor. Since quadratics have degree 2, the maximum number of distinct roots they can have is 2. Quadratics still have interesting root scenarios. Some have two distinct real roots, like x squared minus 4 equals 0, giving roots plus 2 and minus 2. Others collapse to a repeated real root, like x squared minus 2x plus 1 equals 0, which equals x minus 1 squared. So 1 is counted twice. Some have two complex conjugate roots, like x squared plus 1 equals 0, giving I and minus I. In summary, each root brings in a single linear factor, and two factors can only produce powers up to x squared. Quadratics are degree 2, so they can have at most two roots. That is why we never find a quadratic with 3 distinct roots.